All right. So good afternoon, and let's get started because this is going to be. I'll try to keep it as short as possible, but this is overall an extensive topic, so I'm going to try to go over it as precisely as I can. So the objectives for today is basically just to describe the different mechanisms of just gram-negative rod resistance. Take a look at different types of beta-lactamases that are described in the literature and how they basically are implicated in clinical practice. So why are we even having this discussion? Well, that's why. Because really overuse of antibiotics has been a problem. So anytime, it's true, your doctor doesn't know what you have, you get penicillin or some sort of an antibiotic. So just quickly about definitions, it's very important when you're reading literature in general to see how they're defining things as multi-drug resistant. There's no consensus on what a multi-drug resistant organism is. It's one of the goals actually for us to establish. So multi-drug resistance, some institutions define as greater than or equal to two classes that are normally active. Some actually go to greater than or equal to 3. When you're talking about extensively drug resistant, it's basically when you're resistant to everything except 2 agents. And then pan-drug resistant, you're actually resistant to everything. When the word pan means everything. So when people refer to things that are only susceptible to colistin and tigecycline, that would go into the extensive drug resistant category. It's not pan resistant. All right. Other things to consider are also things like clinical resistance, right? So S doesn't always mean success when you're looking at the susceptibility report. An MIC of 64 for Pseudomonas to zosyn is going to lead to clinical failure. So that's referred to clinical resistance. And then some things to keep in mind are also cross-resistance and multiple resistance. You can have one resistance that basically makes you resistant to multiple agents, and that's with the same mechanism, or you can acquire multiple resistances, and that's what happens very often with the plasmid transfers. All right, and this is kind of getting us into the beta-lactamases because that's exactly kind of what they are, the plasmid-mediated ones. So other than having beta-lactamases, other mechanisms of resistance include you have an altered antimicrobial permeability. Those are your efflux pumps. Pseudomonas has them. Altered target sites, that's your penicillin binding proteins. Replacement of sensitive pathways, that would be resistance to Bactrim. Sometimes you'll see it that way when the folic acid actually gets substituted into folinic acid like humans have, and this way you lose the ability of the Bactrim to work. And then basically inactivation of the antimicrobial agent, and that would be our beta-lactamases. And then it's always important to remember that a single organism can have multiple resistances. Okay, so they're carried on plasmids together. So there's 2 types of resistances. There's chromosomally encoded, and these are things that are intrinsically just resistant to the antibiotics, or they can mutate with drug exposure. And then also plasmid mediated. And those are the real problem because they're easily transferable between species. All right, so we're just going to talk about beta-lactamases because you can probably extend this to 3 hours if you talk about all the different mechanisms of resistance and gram-negatives. So anytime you introduce a new antibiotic, the organisms just get that much smarter, so they're working. So beta-lactamases have actually been around for a while. So 1940 was the first one that was identified, and that was found in E. coli. It was chromosomally mediated. It was a sort of an AMP-C type of beta-lactamase, and around the same time also is when staph started developing resistance to penicillin. So that's your first penicillinase was identified. And then now in 2012, we have over 890 different types of beta-lactamases that have been identified in clinical bacteria. So yeah, almost 900. And so if you try to keep track of them, it's kind of hard. There's a website if you'd like. It's there, but we're not going to try to do that. So there's 2 different classification systems for these beta-lactamase enzymes. They can be either classified based on their sequence of how they hydrolyze the beta-lactam, or at what site they work, or actually by the class of the antibiotic. So that's when you get things like cephalosporinases, penicillinases. So this first classification is basically the simplest because it only has 4 categories. It goes into A, B, C, or D. And all your A, C, and D are considered serine beta-lactamases, and then your group B are your metallo-beta-lactamases, which utilize the zinc to hydrolyze. So, but clinically, it doesn't really tell you anything, right? Because it kind of just groups them all together. So, this characterizing it this way with the functional characteristics, it is more subjective because it kind of gives, way for interpretation, but it is clinically more relevant. So it's group 1, 2, and 3. So group 1 are cephalosporinases. They have more affinity for cephalosporins than for penicillins, and that's where your AMPCs would fall into. Okay, so group 2 are your serine beta-lactamases. That's the largest group, and you'll see in a second why. That's where your ESBLs fall into, as well as your KPCs. And then you have your metallo-beta-lactamases, and that's where your Nudali metallo-beta-lactamase would fall into. So if anyone's interested in going through all of them, we can, but we're not going to do so. If you look at just the two, with the two, there's a lot of subcategories. So there's 2A, 2B, 2BE, and they, as the letters are adding on, it talks about more extensive resistance within that class. So my goal was to simplify this for today. Look, if you look at the trends, what's on the rise is actually the class 2 Carbapenem beta-lactamases, and that's because they have the ability to have plasmids and they're transferable. Because the rest of them have kind of remained steady, more or less, but this is and us being able to identify ESBLs kind of does that jump.
Will you say that the class 1, the cephalosporinases, are chromosomally induced?
They are. We'll get into every single one of them. So group 1 are your cephalosporinases. They're class C enzymes, so they're for AMP-C. They're either chromosomal or plasmid mediated, and the chromosomal ones can be inducible. And we'll talk about that a little bit and some of the misconceptions about induction of AMP-C. These are the key differences that I want you to keep in mind. They're actually active against cephalomycins, so AMP-Cs will break up your cephalomycins, unlike your ESBLs. And it's also not inhibited by any of your beta-lactamase inhibitors. So those are the major differences between AMP-C and ESBLs. Like I said, group 2 is your largest group, and it has the widest spectrum. It goes everywhere from penicillins, starting with your group 2A, there's your simple penicillinases, all the way to group 2F and 2DF, and that includes your ESBLs and Carbapenemases as well. And these are mostly plasmid mediated, and they are inhibited by beta-lactamase inhibitors. And finally are your class 3. So they were originally identified as chromosomal, but now have been found in plasmids, which is really scary because now we're having species that have both a KPC type of gene and a metallo-beta-lactamase in one species. So E. coli was just recently identified that had both of them. So. And they are not inhibited by any of the beta-lactamase inhibitors, but they are inhibited by metal ion chelators. One thing to remember, they have very poor affinity for monobactam, so you can still see these organisms be susceptible to azactam.
And is that real?
I don't think I would use it clinically, but they still have a poor affinity for it, but I think with enough of a burden or inoculum effect, that could still be overcome. So,
and many of them have additional
right.
plasmid-mediated genes, so most of them are resistant to oestradiol as well through other mechanisms.
So ESBLs, we're going to talk a little bit about treatment and identification of them. They're defined as any kind of beta-lactamase that you can just hydrolyze third-generation cephalosporins, and they're inhibited by your beta-lactamase inhibitors. And they're found on plasmids with other resistances as well. So that's why when you have an ESBL, you're most of the time resistant to fluoroquinolones and aminoglycosides, because they're all on the same plasmid. They have very large plasmids that they actually transfer. And they're very easily to transfer between species. So what started in E. coli or a CLEB, has gone to other Enterobacteriaceae. And ESBLs will confer resistance to all penicillins, third-generation cephalosporins, and monobactams. They won't confer resistance to your cephalomycins, carbapenems, and they are inhibited by beta-lactamase inhibitors. And the reason I keep on emphasizing that because some of the new data about how what's the way to treat ESBLs. So in terms of detection and treatment of these organisms, so the PCR is a gold standard. I don't know how many places are doing PCR for identifying ESBLs. I don't think anyone is. Most places are using automated systems like the Vitek or Microscan, Phoenix, whatever you may have. The concern with that, remember that they're only been approved for E. coli's and Klebs, so any other organisms you would have to do a manual test if you suspected, and well, how do you suspect it, right? So you would have to really look into it to see. And then the two manual tests you can do are E-test or the double disc synergy test, where you just have the third generation cephalosporin like cefotaxime or ceftazidime because they're more susceptible to these enzymes alone versus having it with a beta-lactamase inhibitor on the other side, and then you look at the change in MIC. And so if your MIC drops by adding a beta-lactamase inhibitor by greater than or equal to 3 dilutions, that's actually a positive test for an ESBL. And look at this was a nice study that looked at all the different automated systems for detecting ESBLs. So, you do have some room as you may be missing a few here and there, and the reason for that is when they have other resistances along with it, like AMP-C, okay, it gives you a very hard time to actually identify them on these systems. So, what are we currently doing, right, if we're going to identify an ESBL? Well, currently, because of the previous guidelines by CLSI, we're reporting all penicillins, cephalosporins, and Astrianem as resistant, but not beta-lactam, beta-lactamase inhibitors, right? Because there wasn't enough data to recommend that. And again, if an organism other than E. coli or Kleb, we really don't have, routinely do anything. So, how is this going to change? And it is going to change. So, 2010, CLSI actually changed all of its breakpoints for Enterobacteriaceae for all of these agents except for cefepime. Cefepime stayed at 8. And the reason for doing that was they felt that clinically your failure was not due to a type of ESBL or AMP-C that you have. It would be based on the MIC. As well as data showed that most of the ESBLs and AMP-Cs tended to be on the higher end of the MIC breakpoint, so 4 to 8. Therefore, that was the reason for dropping it. So these are the current susceptibilities that we use, right? Cefazolin less than or equal to 8. All the cephalosporins less than or equal to 8. Look at that. They're taking them down to less than or equal to 1 for most of them, except there's some talk of actually with cefazolin to bringing it up to 2 or 4 because they think that was just a bit too low, and data has come out that you don't get clinical failure with cefazolin at MICs of 4. Well, I'll show you that they found that most of the ESBLs and AMP-C enzymes are found in strains that have MICs 4 to 8. So if you eliminate that group as being susceptible, your whole issue of ESBLs and AMP-Cs goes away, right? Because they're already resistant. So you're not showing that something is sensitive at a high MIC and leaving it up to the interpretation of the clinician to say, okay, it's still susceptible, and maybe if I push doses high enough, I may still hit that MIC. And we can still do that. Just the idea is we don't have to now routinely screen. So now CLSI recommends that if you're going to go to these new breakpoints, you don't have to screen your organisms for being an ESBL, unless for infection control. So now it's going to be a scary thought, right? So when something does screen as an ESBL positive organism for infection control purposes, but your ceftriaxone MIC is less than or equal to 1, according to the CLSI breakpoint, new recommendations, you can use it. It's going to be a lot of confusion because, for years we've said no cephalosporins, and now we're saying, something else. And this is where it came from. So the data actually shows that, with the new breakpoints, the likelihood of you having an ESBL or AMP-C is not very much. So if you look where most of them were found, all of them are pretty much found at MICs 4 to 8 and then above. So how do we treat ESBLs, right? Historically, it's always been Carbapenems. I mean, I was always taught you use a Carbapenem for serious infections, and that was it. And that came from data that there was high failure to cephalosporins if patients were treated with that. But if you look at the literature, most of the literature that was based on used third generation cephalosporins like ceftaz and ceftriaxone. The studies were extremely underpowered, and the term failure was described very differently in each literature. So one article would call failure if you're still febrile after 48 hours. Well, another one would call it, if your cultures are still positive. So they're very hard to compare the data. So now with us having very limited resources on or what to treat things with, people are looking back to cefepime and zosyn because theoretically, right, if it's inhibited by beta-lactamase inhibitors, why can't we use clinically zosyn? So I'm going to just go through three articles that were either presented as posters at recent meetings or were just published, on which the CLSI made its decision as to not to change the breakpoints for cefepime because it's the only one that actually kept the MIC of less than or equal to 8. So this was presented at ACAC in 2003, and it looked at 43 critically ill patients with ESBL and Urbacter, and they were treated with cefepime versus Carbapenem, and you could see there was no statistically significant difference between the groups, whether you looked at clinical improvement, bacteriological eradication, or mortality rates. There's another study, a poster that was actually presented at ECCMID in 2002, and it just had 44 patients with infections due to ESBL, E. coli, or Klebs, and they looked at bacteriologic eradication, and they looked at cefepime susceptible group and cefepime resistant group that was still treated with cefepime. So this group that was treated with cefepime and it was cefepime susceptible, they had 80% bacteriologic eradication, and in the cefepime resistant group, so all the MICs greater than 8, still about a third of patients still responded. The problem with interpreting this is I have no clinical correlation to it. They're just giving me, culture clearance versus the clinical response. And then one of the more recent articles that was published, it was in 2006, and it looked at, again, using cefepime for ESBL, E. coli, and Klebs, and the results are there. So the,
What was the dose that you used?
2 grams Q8. They're always using the higher doses and that's one thing that they do point out in the CLSI guidelines, that the approved doses for pneumonia in the United States for cefepime are 2 grams Q12. However, we're basing this decision to leave it at less than or equal to 8 on 2 grams Q8 instead of Q12. So yeah, they used to, and you'll actually see that with the zosyn article. So this is actually brand new article. It was just recently published in CID, right? So it was a post hoc analysis that looked at using zosyn for for ESBL bacteremias, and I was like, whoa, okay, this is gonna be bad, right? I'm like, it was kind of an interesting thought. So it looked at a post hoc analysis of 6 published previously studies, and it looked at confirmed bacteremia in these patients with an ESBL treated with either Carbapenem or with zosyn, and they were divided into whether it was an empiric treatment or whether it was actually defined treatment. So in the empiric treatment, there was 103 patients, 72 of which were treated empirically with zosyn it's not really unison, but with a beta-lactam, beta-lactamase inhibitor, and 31 with a Carbapenem. And then for definitive therapy, you also had 54 versus 120. You see the difference? So once people knew this was an ESBL, they ended up switching the patient to a Carbapenem. I think that's where that comes from. So the mortality rates were actually higher, in the Carbapenem group than they were in the beta-lactam, beta-lactamase inhibitor group. This difference wasn't statistically significant. They once suggested for co-founders there was also no difference. But don't forget, the patients who got Carbapenems were probably a lot sicker than the patients who ended up getting the beta-lactam, beta-lactamase inhibitors. So there was something to be said for that. Well, yeah, so 4 grams Q6, 4.5 Q6. So one thing, it's nice, and I'm always open for new suggestions, and as soon as, a little bit more data is available, I think, For less severe infections, this looks like a great option. But all these patients in the study, even though they were bacteremic, their source of bacteremia was either urine or from the biliary tract. So their inoculum effect was not the same as someone who has a bacteremia secondary to pneumonia. So remember that, because a large amount of beta-lactamases can still overwhelm the beta-lactamase inhibitor and make it resistant to Zosyn. So just think about where the source is coming from. And there was a link between MIC antibiotic dose and mortality. So they did use a high dose of 4.5 grams IVQ6. And the 30-day mortality, look at the difference based on the MIC. So if an MIC of the organism was less than or equal to 4 to Zosyn, you only had 4.5% mortality. But once it went above 4, your mortality jumped to 23%. So before we start using Zosyn on these patients, one thing to remember is it a low MIC, and what's the source of the infection? And if it's coming from the urine, I think with an MIC of less than or equal to 1, I think it might be a safe, leap to go and spare Carbapenems. But another thing to remember is, Zosyn is it really more narrow than using ertapenem? Now you're using an anti-pseudomonal agent for something that is not a Pseudomonas. So from an antimicrobial stewardship perspective, is it really, are you really de-escalating, or are you exposing these patients to an anti-pseudomonal agent when they don't need it? So I don't know if I can use ertapenem. I think it's a more narrower drug than Zosyn, right? So, I don't know. It's something to think about. Okay, so we're done with ESBLs. Moving on to AMPCs. Okay, you confused yet? You're going to be right now. So AMPCs are kind of like your ESBLs, except the difference is they're not inhibited by any of the beta-lactamase inhibitors. So they're not going to be susceptible to Zosyn, and also they break up your cephalomycins. And there is two types of AMPCs. There's chromosomally encoded and plasmid mediated. And the biggest confusion is in the chromosomally encoded AMPCs. Alright, so how do we detect and treat these organisms? Well, we can't detect for AMPC. There's no standardized good way to screen for AMPC, so it's really not recommended by CLSI. There's no standard like for ESBLs. So the ongoing debate is, how do we measure these SPICE MP organisms, right? And what's the appropriate way to treat them? I think this is like $1 million question that's been out for a while. All right, what is SPICE MP, right? They're your Serratia, your Enterbacter, your Morganella, your Proteus. Pseudomonas also falls in there, and other non-fermenting gram-negative rods. They're actually found virtually in all Enterbacteriaceae, these AMPCs. The ability to induce them is also in most of them, except for Acinetobacter and E. coli. For some reason, they're just missing a gene that allows them to induce these AMPCs. But they can still acquire it through plasmids, and they do. Induction is reversible. Okay, so when you introduce an antibiotic and it's inducing the production of AMPC, as soon as you remove that antibiotic, it's no longer induced. It goes back to its normal AMPC level production. And the beta-lactams that you introduce are basically are separated into two categories: their induction potential and their stability to the AMPC. Right? So how many times have you heard, can you ceftriaxone, it's a strong inducer of AMPCs? Come on, how many times? This is what I was taught originally too, right? They're not strong inducers. They're actually weak inducers for AMPC. Your strongest inducers are like your Carbapenems that we consider drugs of choice. What they are is they're actually poorly stable to high production of AMPC. So if you have an organism that is producing a large amount of AMPC, that's what makes an issue with using third-generation cephalosporins. And I'll show you where the confusion comes in a little bit. So Carbapenems really have a high potential for induction of this AMPC, but they're also very stable to it. So that's why no one's ever said, oh, you can't use imipenem because it's a strong inducer. No, but it is. It's actually a very strong inducer. So, but clinically, this induction is not what we're concerned about. It's not relevant, because in order for it to be relevant, you would need to give a drug that's both a strong inducer and weakly stable. And we don't really use those drugs, right? You're not going to, that's not what we're talking about. Okay, so what is really clinically relevant and often gets misquoted as induction is the repression of these mutants. So de-repression is basically the ability to select out for a resistant mutant. This is completely independent of antimicrobial agent exposure. It's a spontaneous process that occurs, or it already exists in the whole family of the wild, of the organisms. And once that happens, that's when the organism becomes resistant to third generation cephalosporins and your striatum and things that are weakly stable to large production. And the extent of selecting out resistant mutants actually is species dependent. And I'll show you this. So it's not, let me go through the pictorial of this. This is a little bit easier. So you got a whole family, right, of just like not E. coli, but Enterobacter hanging out there, right? So you have the susceptible one to the drug, and then there's somewhere at the bottom there's one that's resistant. Now you're giving someone third generation cephalosporin that is the susceptible is for. So it's killing all the susceptible organisms, right? But leaving only the resistant one. And now when your cultures come back positive for the same organism, but now resistant to ceftriaxone, you're thinking, oh, it was induced. And it's not because ceftriaxone caused this resistance. It was already there. It's selected out for the resistant organism. So I think that's the confusion, right? And so when we talk about, third generations being strong inducers, actually what they are is they have a good potential for selecting out for resistant mutants. All right, so let's just,
So if this species that's resistant wasn't there,
yeah,
we wouldn't
Nope.
have the resistance.
Nope.
It's not really inducible.
it's,
I mean, the way they called it.
right, well, that's what I mean. So it's ceftriaxone, but even if it is inducible, once you remove, right, it is inducible, but it clinically doesn't make any difference because the drugs that you're using, like ceftriaxone, is a very poor inducer, right? So, and even if it does induce it, when you're using a carbapenem, so what? Carbapenems are stable to them. So induction is never an issue. It's the de-repression that's an issue. It's selecting out for the resistant mutant. Okay, and it's not because you've introduced ceftriaxone. It all of a sudden mutated. They're either there, or it's a spontaneous process. It's just that when you're giving a carbapenem, even if that happens, right? Carbapenem is very stable to AMPCs, so you don't, you're not selecting out for those mutants. Okay.
Yeah, so correct if I'm wrong, but a de-repressed mutant, it's like the induced organism, but it won't go back to its to that baseline state. It's permanently locked in high MC
Right.
production.
Right.
Unless you stop using it, no?
No, that's for the inducible. That's for the inducible, and then for the de-repressed, there's no other organisms that are there that are sensitive. All you've done now, you've isolated the resistant organism, and that's what's growing, because you've killed out the susceptible ones. All right, and this is where this landmark study came from, right? This was in 1991 by Chow and colleagues, and basically you looked at the results of Enterobacter bacteremia, right, and clinical failure with using a third generation cephalosporin. And he found that 19% of all Enterobacter bacteremias actually ended up having failures or breakthroughs with now resistance to third generation cephalosporin. So the suggestion by the author was, in all the organisms that have the ability to induce AMPCs, okay, we're going to don't use third generation cephalosporins. Little problem with that was, one, it was a pretty small study. It had 31 patients only that were treated with the third generation cephalosporin. Didn't include any other organism in the study, only Enterobacter, and actually generalized this conclusion to the rest of them. And only patients with bacteremia. I mean, not all infections are created the same, right? So 20 years later, has anything changed at all, right? Any new data out there? And there is. There's few good studies that actually looked at this AMP-C and the ability to select out. So this was a nice review done in 2002. What's important to remember that, again, what we talked about, the resistant mutant pre-exists in the susceptible bacterial population, okay, neither induced nor obtained by mutagenic effect on the Oh, that's the yeah, that's one of the things that got it. So, anyways, it's neither induced nor is it due to the antibiotic mutating it. It's already there. So, emergence of resistance to third generation cephalosporins has to be compared to other drugs as well. Like when you're treating an Enterobacter with the quinolone, what is going to be your resistance rate then? How many times you break through on that, or an aminoglycoside? And look at this review, right? So for Serratia, Enterobacter, and Citrobacter, when patients were treated with cephalosporins, you had 9.9% versus Cipro, which is 5.9, versus aminoglycoside, which is 13.9. So all drugs have the ability, it's not just third generation cephalosporins that may have failure. So this was a prospective study that assessed what was the incidence of breakthrough resistance. The primary endpoint was emergence of resistance during antimicrobial therapy. And basically, the infections were broken up into Enterobacter. There was also Serratia, Citrobacter, and Morganella. There were 732 patients that were treated, right? And the overall incidence of emergence of resistance during therapy was 1.9%. So only 14% of patients ended up breaking through with a resistant organism. Okay, out of those 14 patients, okay, you had 11 that broke through on the third generation cephalosporin, but out of all those 14 patients, 13 had an Enterobacter. So you cannot generalize what happens with Enterobacter infections happens with the rest of them, because none of them, there were 0 cases of breakthrough for Serratia, 0 cases of breakthrough for Morganella, and 1 patient broke through on the Citrobacter. So the takeaway message from this is that not all spice MP organisms are created equally. Okay, so we shouldn't really group them together. Enterobacter is its own, This study specifically looked at Enterobacter and looked at its 30-day mortality rates on patients who were treated with third generation cephalosporins. And unlike our landmark trial that showed, 19% rate of actually breakthroughs, there were actually 3 patients that broke through at a resistance rate of only 4.5%. So, it does occur, but these were Enterobacter, and they were, bacteremia patients. So one thing to remember, so like I said, the takeaway message, they're not all the same. It's species and strain dependent. It's inoculum effect dependent as well. So treating a bacteremia with Enterobacter is not the same thing as treating a UTI with Enterobacter. So, things to remember, and Serratia is not an Enterobacter. And they're antibiotic dependent. All right. So plasmid-mediated AMPCs are easy because there's nothing to induce. When they transferred, they're already going to be resistant as they are, and you can actually get it in organisms that normally don't, normally not inducible, and that would be like things like E. coli. They just transfer it to them, and that's why you see E. coli's with AMP-Cs. That's not because they can do it on their own, because, they got it from someone else. All right. I don't know if you can see that, but I think it's hilarious, right? So I'm actually getting close to our, worst offenders, right? We're gonna start talking about the Carbapenems. We're good. Done.
So if you see an E. coli that is with high MICs to cephalosporins and resistant to piptazo, you can suspect an AMPC from plasmid-mediated.
Yep. Or also looking at cephalomycins helps. If it's resistant to cephalomycins, that would also make you really highly suspicious. And
especially if it's resistant to quinones too.
yes, and yeah, it's an issue.
You might still use them, but if it's a short-term infection, but if it's a long-term, you would avoid using the third generation stuff.
I would look at the MICs. So at lower MICs, your rates of breakthrough are not very common because, again, you're selecting out for resistant mutants tends to be a little bit of higher MICs, 4 to 8 actually for the most part. So if I have an infection with this, ceftriaxone MIC less than 1, cefazolin MIC less than 4, and cefepime less than 1, I'm not very concerned that it's going to become very resistant because even your first generation cephalosporins are susceptible.
And even if it's a long, like osteomyelitis, for example, 6 weeks, or does the duration make you?
it's not. It's remember, it's spontaneous. It doesn't matter what if the antibiotic is there or not. It's not selecting out for it because it's already the organism is already either there, that resistant one, or it just happens spontaneously. So it's not like you're underdosing. Right, it's not like you're underdosing this patient, therefore selecting out for resistance because of low exposure to the drug. It's not like that. It's already there. It's kind of just happens. They're smarter than us, right? The bugs are just, you know. And okay, so talking about carbapenems, you know something's bad, right? When the media starts reporting it. First it's MRSA, new bug, then talking about, the new Beta-Lactamase. So new superbug from India, right? It really isn't that new, just has a new name. Like Beta-Lactamases have been around forever, and we know about them. We had them in New York. They're coming to Florida. They're everywhere. So it's just kind of interesting how the public, once something's a problem, the public hears about it on TV or on the news, right? So Carbapenems is kind of just a general grouping. You put it all together, but there's three types. There's your OXA beta-lactamases, which are chromosomal. You have your serine carbapenems, which are the most common ones, and those are plasmid mediated, and that's your KPCs types. And then you have your metallo-beta-lactamases, which are plasmid, okay? So really scary when your two worst kind of beta-lactamases are transferable between each other. So OXAs originally came from their ability to hydrolyze oxacillin. Yeah, they're way past that, right? So they're mainly chromosomal, and they're found in non-fermenters like Acinetobacter, Pseudomonas. The thing with them is, with OXA type beta-lactamases, is they may still screen susceptible to carbapenems because it takes longer for them to show their full ability to hydrolyze it. So very sensitive to hydrolysis by OXA is ertapenem. So I'm a strong believer that every gram-negative panel needs to have ertapenem on their susceptibility. You can't practice otherwise because, it will show resistance to ertapenem and still look susceptible to imipenem and meropenem. And that should be your first hint to go ahead and set up a modified Hodge test. Or even if the MIC to ertapenem is anything above 1, you should start thinking about a modified Hodge test. All right. So the serine carbapenems are your most common ones, and they hydrolyze most beta-lactams, including carbapenems. Initially, it was just isolated in a single, club, and then people thought it wasn't going to be an issue, right? Because it was in a chromosome, and nobody really thought that it was going to be plasmid. Well, it spread in New York, one of the first places that identified the KPC2, because first there was the KPC1 that was identified, then New York City identified KPC2 and was responsible for the biggest outbreak of it. And now we found out the KPC1 and KPC2 were the same, so now you look at just KPC2 and 3, which are most common in the United States. And they're not only in klebs, right? So just because they have that name, they can be in any of the Enterobacteriaceae. So the MBLs thought they're never going to be a problem, right? Because they're only on they're chromosomally mediated, they're not on plasmids, they're really on organisms that already have it, that's, they're encoded for like Stenotrophomonas. That's how it's resistant to, Carbapenems and Aeromonas. So nobody ever thought it was an issue, except for when they became able to be transferred on plasmids, right? So MBLs have now been identified to be plasmid mediated and now can spread between all the species of the Enterobacteriaceae. So detection and treatment. So when do you suspect that you may have a KPC? Like I said, if you have an Enterobacteriaceae that is resistant to extended spectrum cephalosporins, right, or has very high MICs, and carbapenem MICs in general are greater than 2, and for ertapenem greater than or equal to 1. That is your light to go ahead and start suspecting it. And how do you detect them? Basically, it's the modified Hodge test. It's 100% sensitive. It's not very specific. Can't tell you which one it is, but if it's positive, you have some kind of carbapenemase. So, has anyone ever seen a modified Hodge test? Yeah, right, okay. So, you can and just remember that you can have a carbapenem resistant organism with a negative Hodge test. That's because they probably have an AMP-C along with poor, just efflux pumps, and that makes it resistant to the carbapenem. But so the positive Hodge test is where A is. So you see, I mean, you're all familiar with it, right? I don't have to go into discussing it. Okay. All right, so now you identified it as being a carbapenemase producing organism. Now what? What does your lab do? They don't have any guidance from CLSI. There's not enough data to recommend to calling it resistant. So you kind of just know about it, and it just says, Hodge test positive, right? Most places don't convert. So so CLSI said, okay, we got to do something about this. Just like with the cephalosporins, there's new revised breakpoints. So everything from imipenem, meropenem, that was less than or equal to 4, susceptible, now is less than or equal to 1. Okay? So that kind of cuts out a lot of your carbapenemases, because carbapenemases tend to be in the MICs from 2 and up. Ertapenem, first there was talk about making it 0.25, and said, okay, that's pushing it, so now that it's 0.5 would be the cutoff. All right, and this is the data as to why they did this. So with the new CLSI breakpoints, look at an imipenem less than or equal to 1, you had 0 organisms that were carbapenemase producers. Meropenem 1.2%, ertapenem less than 0.25 was 0%, and doripenem was 0%. So that's where those cutoffs came from. Now you don't have to, again, like with the ESBLs, you won't have to screen anymore for carbapenemases. And this is the same idea. So drug of choice, right? What do we treat carbapenemases with? No one has a good answer, right? Because it's either things that are sensitive in vitro is colistin, tigecycline, minocycline, using them together, adding rifampin for synergy. It's really, there's really no good data about how to treat carbapenemases. This was really helpful, all right? This is a brand new trial, like a retrospective, actually, review study that came out of St. Luke's in New York. They looked at, these were KPC confirmed bacteremias, and they looked at monotherapy versus combination therapy in patients who were treated with monotherapy versus combination therapy, and looked at overall survival and mortality. So there's 41 patients with KPC bacteria, so 41 bacteremias that are KPC confirmed, and they looked at 28-day crude mortality, and then actually they looked at and overall mortality was 39%. When once adjusted, they looked at the 28-day mortality of combination versus monotherapy. So combination patients who got the combination regimen had 13.3% mortality versus patients who got monotherapy had almost 58% mortality. So the most common combinations was either colistin, polymyxin B plus carbapenem, tigecycline plus carbapenem. And in that group, because there was other combinations, but when you looked at these specific combinations, overall mortality was 12.5% in those patients, so significantly lower. So monotherapy with colistin or tigecycline, 28-day mortality for both of them was 66.7%. Look at tigecycline monotherapy mortality; it's 80%. Okay, so next time anyone tells me they want to use tigecycline monotherapy for a KPC, I think I'll refer you back to this article. Okay, so 80% mortality in these patients. One, using tigecycline for bacteremia doesn't seem like a great idea, and then 2, using it for a KPC. And one thing to remember, these patients who received the carbapenems were resistant. The only things that they were susceptible to were colistin and tigecycline. So.
And all those, the tigecycline group with 80% mortality, those were all tigecycline
susceptible. They were all tigecycline susceptible.
I guess by using carbapenems on top of colistin plus or minus rifampin, if you're using it like good infusion and good dose, you may be able to overcome the carbapenemase.
that.
attacking Colistin using another method of action.
Right, and plus the issue with using colistin monotherapy is colistin is first bactericidal, but then it loses it very rapidly allows for bacterial regrowth. So in a very short time, it doesn't sustain its cidality over a long period of time. And when you're using it as monotherapy, you end up, so you're killing your organism and then it regrows very fast, right? So you're killing it and then it grows really fast. So it takes a while to actually get rid of it, and then we don't really know how to dose colistin very well either. So are you under treating? Are you? So no one knows.
What do you use colistin and tigecycline together at all?
I don't use tigecycline ever.
No, but-
Yeah, no, you can. Yeah, so that's what was the most common. No, I guess you can. I mean, people have done it.
And then, like, what carbapenem they use and how they dose it?
It was, I don't, as long as you can push the doses, anything you can do over a continuous infusion or prolonged infusion would be your best bet. So like doripenem tends to be the most stable to carbapenemases. Ertapenem is the least stable to carbapenemases. I would, my preference would be meropenem or doripenem. In what's been being done in places that have colistin resistant organisms and tigecycline resistant organisms, what I've seen done, and microbiologically it's great. Survival is still horrible for these patients, but we give ertapenem followed by continuous infusion or prolonged infusion of doripenem. So ertapenem serves as like a suicide substrate, right? So it kind of throws itself out there. It's the least stable, and then once the carbapenemases are there, you kind of go ahead and just give another. Yeah, you give the more stable carbapenem. So
The question is,
Those studies one with continuous infusion?
the dosing here, they're mostly prolonged infusions, or they're given high doses and prolonged infusions. Because a lot of places can't do continuous infusions because of logistics issues and nursing issues. So what's done is just high dose prolonged infusions over 4 hours.
What was the sources? Are they urine?
So most of the patients actually had pneumonia was the most common source, which was actually kind of nice to see that it wasn't low burden. They were for the most part hospital acquired and healthcare associated. None of them came from the community. And I don't know if you're familiar with St. Luke's. St. Luke's has extremely sick patients as well. Like, so there were transplant patients included in that patient population, and the combination group had more transplant patients than the monotherapy group. So that, I think, even skewed the results more. It would have looked better if the groups were more balanced, because when you have heavily more transplanted patients, your results are not gonna, So just in summary, so the prevalence of beta-lactamase and gram-negative bacteria is increasing, and they're mostly plasmid mediated. Hopefully, we're going to see the CLSI changes. Until the FDA catches on, it might be some time. That's why your labs are still using the old ones. Carbapenems have historically been the drugs of choice for ESBLs, but that's how we actually got our KPCs. So maybe some thought about certain infections and just using Zosyn and using Cefepime in the future. And not all organisms that can hyperproduce AMCs should be treated equally, right? So they're not all the same, so you can't generalize. And carbapenem resistance is on the rise, and you have really a few agents and really limited data on what's the optimal way to treat it. So I'll take questions, but I'll leave you with this. So World Health Organization, World Health Awareness Day 2012 was all focused on antibiotic resistance. And this is the first time that people have referred to this as post-antibiotic era. So remember before penicillin, people were dying, and then we got penicillin? Well, we're going to that pre-penicillin because we've used up all our antibiotics. And this is really a call for, can we please get together and make something from a government level that would, require production of more agents. And it's not a profitable business to make agents, I guess, against resistant organisms, right? Because you're only targeting a small group of patients that can receive them. And that's why your broad spectrum antibiotics get approved for narrow spectrum infections, right? That's why your, cephalosporin has, these, cap indications. That's why it's not profitable to actually keep them for. So I thought this was nice that there's, IDSA, it was World Health Organization, IDSA, SHEA, that all got together and kind of did this, which was great. And here are all the references, okay, if you're interested. All right, questions? No?